So now let me discuss how panel data could be used in estimating an econometric model. Now, try to look at the data matrix first. You have some rows, you have some columns, and the matrix. Okay. So you can take a particular row in estimating a regression model. So if we consider a particular row, how many rows you can get? T number of rows, because you get one row for each time period. So the estimate obtained from a particular row will be similar to the cross-section measure in linear regression model. Similarly, if we use information only along a particular column indicates the variation of the variable over time for a particular cross-section unit. So if we want to utilize only a column, we will get a model similar to the time series model. So if you have a panel data, you can use only a particular row or different rows separately, or you can use a particular column or different columns separately. When you are using a particular row, you will get a cross-section regression model. If you use a particular column, you will get a time series econometric model. The third alternative, you can use the matrix as a whole. So when you use the matrix as a whole, you will get a panel data regression model. So when you have a panel data, if you want, you can use it simply as a cross-section model. You can use it simple as a time series model, or can use it as a panel regression model. So let me look at how we can utilize panel data in different types of models. Okay. So in the second session today, we start with panel econometric models with panel data. Now let me start with a extreme case, fully unrestricted model. Fully unrestricted model means, as I have mentioned you, in a panel data there are two dimensions, variation across the rows or variation across the column. Okay, so first of all, suppose we are interested with the variation across the column, that is the variation across the cross-section unit. So in your sample, total number of cross-section unit is equal to capital N. Okay, so you have n number of columns, capital N number of columns. And normally the cross-section units in your sample are heterogeneous. Okay, so if we consider all the cross-section units are perfectly heterogeneous, that is, one cross-section units are completely different from the others. So if we use this kind of assumption, we have a model which is known as the fully unrestricted model. So fully unrestricted model means we do not use any restriction. What kind of restriction? Restriction means, just think about the classical assumptions used in our regression model. Zero mean assumption, constant variance assumption, zero covariance assumption, etc. So constant variance assumption indicates homoscedasticity assumption. So the assumption of homoscedasticity is one kind of restriction we are using. The assumption of non-autocorrelation, another kind of restriction we are using. So when we estimate a model, we impose some kind of restrictions. Okay. So suppose First of all, we do not impose any restriction. So in that case, we get a fully unrestricted model. Now, fully unrestricted model can be obtained in two ways. One form is the cross-section regression model. So if we want to estimate a cross-section regression model, in that case, we can utilize between group variance and between group covariance. So by using between group variance and between group covariance, we can calculate the cross-section regression model. I have already mentioned to find out a regression coefficient, we need covariance measure as well as variance measures. So if you use between group covariance measure, if we use between group variance measure, you can get purely cross-section regression model. Similarly, we can get time series regression model. So if we want to have a time series regression model, in that case, we can use only within group variance and within group covariance. So among the three types of variance and covariance we are discussing, if we use between group variance, if we use between group covariance, we can get a purely cross-section regression model. So in the case of a regression model, purely cross-section regression model, you are using the variation along a particular row. So for a particular row, the information varies between group, information varies between the cross-section unit. That's why this kind of model normally is obtained by using between group variance and between group covariance. Now in a time series model, how do we get a time series model? Think about a particular column. So along a particular column, there is no variation between the cross-section unit. You are considering a particular cross-section unit. So there is no question of variation across the cross-section unit. But here we are considering only the variation over time. So variation over time, or in a time series regression model, we are utilizing the within group variance and within group covariance measure. Okay. So to start with, suppose we are considering a multiple linear regression model like this. You are familiar with this kind of model. Yi in the case of cross section, we have used earlier. Yi is equal to xi prime beta plus ui. But here we are using the suffix it. Yit is equal to x prime it beta I plus uit. Just concentrate on beta I. Normally we use beta. Now here we are using beta I. What does it mean? What is beta? Beta is a regression coefficient. So beta I indicates this regression coefficient will be different for different value of I. In other words, if we specify the model in this way, we can get a value of beta hat for beta hat separately for separate cross-section unit. Okay, so this kind of model is called a fully unrestricted model in the sense that the all cross-section units I is equal to 1 to n are assumed to be heterogeneous. For that reason, we are estimating regression coefficient separately for the cross-section units for each cross-section unit. So if we specify our model in this way, where beta is defined in this format, beta is a vector of the regression coefficient. So if in your model, if you have k number of regressors, so you have to estimate k number of regression coefficient, beta 1, beta 2, beta 3, beta k. So these k number of regression coefficients are different for different cross-section units. That's why we are still keep the suffix I everywhere. So beta prime I indicates the regression coefficient for a cross-section unit I. So how to get beta prime I? You will get beta prime I by estimating this model only by considering the variation along a particular column. So one column, you will get one value of beta for one value of I. So how many columns you have? The number of columns is equal to the number of cross-section units. So if we estimate this regression model by using the variation only a particular column, you get capital N number of regression equations here. And we are estimating separately N regression equations only by using the time variation. So this model is nothing but our conventional time series model, one time series regression model, one for each cross-section units. Okay, so if we use the model in this way, we can get different value of beta hat for different cross-section unit. So how do we get beta hat? The value of beta hat will be S XXW inverse S XYW. So this value of beta hat is similar to the familiar expression for beta hat like this. You know the value of beta hat by applying OLS or MLE, you will get x prime x inverse x prime y. So what is x prime x? X prime x is a variance measure of x. X prime y is a covariance measure of x between x and y. And as they are in vector sense, we have to take the inverse and multiply it with x prime y. If you have a simple linear regression model, the formula for beta hat becomes sum of xy divided by sum of x squared. So this formulation is similar to the simple linear regression model, sum of xy by sum of x squared. So this value of beta hat in this model, you get how many beta hat? N number of beta hat. So beta 1 hat, beta 2 hat, beta 3 hat. In this way, we can get beta n hat. So how to get beta 1 hat? Just by considering the first column in your data matrix. So by taking the first column, you can calculate within group mean from the first column, and you can calculate within group variance from the first column. You can calculate within group covariance from the first column. So by utilizing the variation only over the first column, you can get beta 1 hat. Similarly, by using the variation along the second column, you will get beta 2 hat. So in this way, we can calculate beta 1 hat, beta 2 hat, beta 3 hat, up to beta n hat separately by estimating the model by using the column-wise variation. Okay, so this unrestricted model is nothing but our conventional time series model. So to estimate this model, we have to follow all the steps as we have discussed in the part of time series. That is, in that case, we have to examine the stochastic behavior, stationary or non-stationary, each and every variable you are using in your model. So if they all are stationary, there is no problem. You can apply it by you can estimate it by applying OLS. But if the variables are non-stationary, in that case, you have to consider the possibility of co-integration. And if the variables are co-integrated, in that case, you will get the meaningful estimate of beta. Okay, so these are the similar for the time series model. That's why we are not explaining in detail. So in the fully unrestricted model, we can get different value of beta hat for different cross-section unit. So in that way, we are considering all cross-section units are perfectly heterogeneous. In what sense? Suppose Y denotes consumption, X denotes income, for example. So in that case, beta indicates the marginal propensity to consume MPC. So MPC indicates the responsiveness of consumption expenditure due to 1% increase in income. So if beta is different for different cross-section unit, that means the value of MPC will be different for different cross-section unit. So if the value of MPC are different, that is the cross-section units are not similar. So if the cross-section units are purely different, in that case, you will get different values for marginal propensity to consume. Similarly, for the other type of models, you can interpret this model in this way. So this is one extreme case where we can think about the cross-section units are purely heterogeneous or perfectly heterogeneous. In the another extreme, suppose all cross-section units we have in the samples are purely homogeneous. So there is no heterogeneity among them. So if we assume all the cross-section units are homogeneous, so this is the restriction we are imposing here. That's why this model is known as fully restricted model. Why fully restricted? Because we are assuming all cross-section units are perfectly homogeneous. So if perfectly homogeneous, so in continuation with our above example, the MPC will be the same for all cross-section units. So suppose our cross-section units are the countries, country 1, country 2, country 3, country 4. So in our above model, in the unrestricted model, we have different values for MPC for different countries, because we are assuming that all countries are perfectly heterogeneous. Okay, but in this kind of model, second type of model, we are imposing a restriction. What is the restriction? Restriction is all countries are perfectly homogeneous. So if all countries are perfectly homogeneous, so there should be only one MPC representing all countries together. So in that case, just look at this model, YIT is equal to XIT prime beta. So we are considering only one beta to represent all the cross-section units. So in that sense, we are considering all the cross-section units are homogeneous. So under this assumption, the homogeneity assumption, we can formulate a regression model like this: YIT is equal to XIT prime beta plus UIT, and this kind of model is called the pooled regression model. Pooled regression model. So in this pooled regression model, we can utilize the concept of covariance and variance. Which kind of concept we can use here? The total variance, the overall variance, and the overall covariance. So we are discussing three kind of variance covariance. Among these three, we can use between group variance, between group covariance for cross-section model. We can use within group variance, within group covariance purely for the time series model. And if we want to use a pooled regression model, fully restricted model, in that case, we can use the overall variance and overall covariance concept. So in this way, different types of concepts could be used in different types of model if we have a panel data. Because in a panel data, we have already mentioned in our previous class that we have more breathing space. We have a lot of scope for variation. We can allow the variation of the variables across the cross-section unit. We can allow the variation of the variables over the time period, or we can allow the variation of the variables together with cross-section unit as well as over the time period. So in this fully restricted model or the pooled regression model, we can utilize the variation of the variable together across cross-section unit as well as over time period. So this model is nothing but our familiar multiple linear regression model. Difference is we are using a suffix IT to denote the panel data, because the panel data we have discussed have two dimensions. One is the cross-section dimension, another is the time dimension. So the variable Y varies across I over T. Similarly, the regressors can vary across I over T. So this is our familiar multiple linear regression model, and the basic assumptions on the random disturbance. So U denotes the random disturbance term or the random error term, and we retain the assumption, the classical assumptions, that is the expected value of U equal to 0 mean condition. Variance of U is equal to constant, that is homoscedasticity retains. Covariance of the random disturbance will be 0, that is we assume that there is no autocorrelation. Okay, so we keep the assumptions we need for a linear regression model intact in this case also. So under those assumptions, you can easily calculate the population regression function or the conditional mean function in this way. If you take mean expectations on both sides, the expected value of the random error term will be 0, and you will get the conditional mean like this. And you can apply the OLS, ordinary least square, to find out the value of beta hat. So beta hat will be equal to the same. The x prime x inverse x prime y. This x prime x is denoted as sxx, and this x prime y is denoted as sxy. That is x prime y is the sum of of the cross product term x and y, and this is the sum of square of the x. So x prime x is equivalent to sxx, x prime y is equivalent to sxy, and we have used these symbols when we discuss the multiple linear regression model in a cross-section setup in your earlier class. So by using this notation, you can get beta hat is equal to sxxt inverse sxyt. That is the variance. The variance component is obtained by considering the total mean. So this is the total variance and this is the total covariance. So by using total covariance and total variance, you can have the OLS estimate of beta, that is beta hat. As I have already mentioned, in the case of pooled regression model, we can utilize the concept of total variance and total covariance. Okay, so up to this, there is no problem, and they are similar to our the conventional case as for the multiple linear regression model. Now, the basic problem in any linear regression model when we use cross section or time series, whatever may be, the basic problem involved in a linear regression model is the problem of endogeneity, and this is a serious problem we have to face in our real life data. So when we are using real data in estimating a model, this kind of problem may appear in most of the cases, the problem of endogeneity. What is the problem of endogeneity? I have mentioned it several times earlier. Problem of endogeneity appears when the random error term U is correlated with the regressors. So when the regressors and the random errors are correlated, then the problem appears, what is known as the endogeneity problem. So if endogeneity problem appears in your model, the OLS estimate beta hat will not be unbiased. So in that case, the beta hat will be biased. And why the value of beta hat will be biased? Simply because in your data, unobserved heterogeneity appears. So in your real data, in your sample you are using for estimation, contains a lot of heterogeneity, and many heterogeneity are unobserved. We cannot observe by looking at the data. So because of this unobserved heterogeneity, we have to face the problem of endogeneity. Okay, but in estimating this model, we assume that the random error are homoscedastic. What does it mean? Homoscedastic random error implies your cross-section units are homogeneous. So there is no scope of heterogeneity across the cross-section unit. So the basic assumption in linear regression model is the homoscedasticity, and the homoscedasticity assumption requires that the cross-section unit should be homogeneous. So indirectly we assume in our conventional linear regression model that the cross-section units are purely homogeneous. So under this restriction, or under this assumption, we can use OLS. So when we use OLS, we assume that the variance of the random error is constant. That is, the cross-section units in your sample are homogeneous. And if they are homogeneous, there is no scope of correlation between X and U. And in this case, theoretically, we get unbiased estimate. Expected value of beta hat is equal to beta. So this kind of unbiasedness will be obtained if your sample contains no source of heterogeneity. But in reality, you cannot ignore heterogeneity. So you need to consider the heterogeneity. And as the degree of heterogeneity will be more, the deviation for unbiasedness will be more. Okay, so for that reason, the linear regression model with a cross-section data, the beta hat in reality, in many of the cases are not unbiased. Okay, and if you look at closely this model, there is no difference between our conventional multiple linear regression model to the pooled regression model. The only difference is in a conventional multiple linear regression model, we are using the suffix I in both sides. In our panel data, we are using the suffix IT. That is, here we have more information, we have more data point as compared to the conventional cross-section model. So the only difference is we are estimating this model by using more information, but in our conventional cross-section model, we are estimating this model with a limited information. So this is only the basic difference between the pooled regression model and our conventional multiple linear regression model. So in this pooled regression model also you will get the beta hat will be biased, but the degree of biasness will be lower as compared to the conventional cross-section multiple linear regression model. So whatever may be, biasness will be there, and the biasness will appear because of the unobserved heterogeneity. And you cannot ignore this problem if you have a cross-section data or if you have a time series data. In other words, if you want to estimate this multiple linear regression model with cross-section data, or if you want to estimate this multiple linear regression model with time series data, you have to face the problem of heterogeneity. And you cannot eliminate this problem in a simple manner. But if we have a panel data, we can eliminate this problem of a heterogeneity. But still at this point in the pooled regression model, we cannot eliminate this because even in this model, even in the pooled regression model, although we are using the full sample, the data matrix as a whole, we are not utilizing the basic benefits that can be obtained from the panel data. We are just using the full sample set to get more robust result, but still now we are not utilizing the benefits of the panel data because we are still assuming that the cross-section units are homogeneous. And this assumption will be contradicted to the reality we have to face. In reality, we have to face the problem of heterogeneity. So how do we eliminate, or how we can eliminate this problem? There is a little scope for elimination of this problem if you have a cross-section or time series data, but we have a lot of scope to eliminate this problem. We have a panel data. So how to eliminate this problem? Let we try to understand it. So now we are entering into the third possibility, partially restricted model. So we have started with the fully unrestricted model, and fully unrestricted model is equivalent to the time series model we have. And then we have discussed the fully restricted model. This fully restricted model is roughly similar to our conventional cross-section multiple linear regression model. They are similar. And now we are introducing another kind of model, econometric model, partially restricted model. Partially restricted model means the cross-section units in your sample are heterogeneous, but not fully heterogeneous as we are considering in the first case. So the number of countries you are considering, all countries are not perfectly homogeneous, that is, countries are heterogeneous, but obviously all countries are not perfectly heterogeneous. There may be some similarity between the countries. So countries will be homogeneous partly and partly heterogeneous. For that reason, we can impose the partial restriction. Okay. And in this partial restriction, or in this partially restricted model, we have what is known as the error component model. So this is the basic benefits we can draw from the panel data. So in a panel data, in true sense, we can estimate a model which is known as the error component model. So now let we try to understand the meaning of the error component. Error means the random error used in a linear regression model, U. So in this random error, there are a lot of factors present, and all factors are unobserved. So in U, or in the random disturbance, we are considering those factors which are unobserved, but which have some possible effect on Y. So they are clubbing together in the random disturbance type. Okay. Now, let we separate out some components of the error from the random disturbance type. In other words, let we decompose the random error. Okay. So we are trying to look at the different components of the random error. So we are decomposing the random error. So we can decompose in two ways. Out of the whole part of the random disturbance, suppose some part is purely random and we have nothing to do, but some part is may be random or may not be random, but unobserved. And as they are unobserved, we are putting them in the random component U. Okay. So in a panel data, you have a source of variation, two types, one across the cross section, another one over time. So heterogeneity may appear across the cross section units may be heterogeneous, or time points may be heterogeneous. So there are two sources of heterogeneity in your data, in your data matrix. One source is the heterogeneous across the cross section units. Each cross section unit are heterogeneous. Second one, the data set are heterogeneous over time. That is, the data set you have at different point of time are different. Okay. So if we consider this kind of heterogeneity separately, we have an error component model. So in an error component model, first of all, we have to decompose the random error into two parts. One part responsible for unobserved heterogeneity. And this unobserved heterogeneity may be involved in the cross-section unit or may be involved in the time dimension. And another part is purely random. Just look at this simple expression. So UIT was the random error in the multiple linear regression model in here. So UIT is the random error. Now we are decomposing this UIT in this way: mu I plus epsilon IT, or UIT is equal to lambda t plus epsilon IT. So we have a few minutes left, so it will be stopped anytime. So we can again restart our session after finishing this one. So till now we can continue to discuss. So this random error is decomposed in this way: mu I plus epsilon IT, or UIT is equal to lambda t plus epsilon IT. So in earlier, this is the total error, and we are decomposing. This is the first component, this is the second component. In the first component, just try to understand, we have used only suffix I. That is, this component varies only across the cross-section unit, not over time. Similarly, in the second formulation, we have written only the suffix T, not I. So in this formulation, the heterogeneity varies over time, not across the cross-section unit. Okay. So in this way, we can decompose the error either across the cross-section unit or by taking